All right, I've had lots of people ask me questions about how to do annuities, so I thought I'd knock up a quick video about it. So, for this video, I am going to assume that you know what an investment and a loan are and what the difference between them is. I'm also going to assume that you know how the compound interest formula works. That's Unit 1 content, so we covered it in Year 11. And I'm also going to be doing a little bit of recursion in this video as well, so I'm sort of assuming that you know your way around sort of Unit 3, Topic 3, which was about geometric and arithmetic sequences. If you don't, well, maybe let me know, and I will maybe make some other videos about those. But also, you'll probably be able to get by in the video without knowing all those things. Just kind of follow along as best you can. So, an annuity is any investment or loan that involves regular payments of some kind. Okay. This is different from what we've covered when we looked at things like simple and compound interest, because there were no regular payments at all. Okay, this is where we investigated both investments and loans and the difference between them. And you will see that there were no sort of regular payments. Okay, so let me give you an example. Here's your sort of typical compound interest question. Let's say you had an investment of $10,000, okay, and the interest was 3.9%, compounding monthly. And you invested it for 4 years. Okay, so if you were to do this like a normal compound interest question, you would basically get your compound interest formula like this, where I would be the interest rate as a decimal, and then divided by 12 because it is compounding monthly. So the variable I there stands for the interest rate as a decimal per compounding period. So that would give us an interest value of 0.00325. And then our N value is the total number of compounding periods. So if that's 4 years, 12 months in each year, that's 48 compounding periods, or 48 months. So if you pop all that into your calculator, you end up with a total value of $11,685.31. Lovely. Now, that's not a very authentic situation. Some people do just have $10,000 lying around and they pop it into a term deposit or something like that. But for most people, when we're saving, we tend to put aside a regular amount of money each month or each week, and save money over time. And if you do that into a savings account, not only are you accumulating the money that you're putting in there every month or week, but you're also earning interest on top of that. Okay, so what I just did there was your typical compounding interest question, but what you would see in a more authentic situation is something with regular payments. Okay, so maybe you might see something like a person puts in to an account $200 every month at 3.9% compounding monthly and they do that for 4 years. Okay, well, that's what we call an annuity. Okay, and even better still, this is known as the deposit phase of an annuity. Why is it called that? Because you are making deposits. Okay, deposits are those regular payments that we put into our bank account to accumulate the interest and the money over time. Okay, now if I were to turn that into a recursion relation or a recursive rule, it would look a little something like this. This means the next term is found by multiplying the current term by the interest rate plus 1 because we're increasing it by this percentage, okay, and then we are also adding $200. And in this case, we're starting from nothing, okay, so no lump sum, just starting from nothing, and every month you're adding in $200, and as that $200 accumulates, there's also some interest that's accumulating, okay? And if you pop that into an Excel file, which I have prepared earlier, you can see in my formula here, I've set up that recursive relation, and you can see this investment growing over time, which is great. Now, you can barely tell, but there's actually, that line is not straight. That is a curve, okay? So just to show you that, I have exaggerated the interest rate, and you can see that it is, in fact, a curve, okay? So bear that in mind. It's always going to be a curved line because of that interest rate we were talking about, okay? And so you can see starting at 0, and then the first month you add your $200, and then the next month you add your $200, but you can see we've earned 65 cents of interest, which doesn't seem like much, but it adds up over time, okay? So if we scroll down to 4 years later, which is 48 months, you can see we've accumulated just over $10,000 there, okay? Now, you're probably wondering, what do you do if you don't have a handy Excel spreadsheet with you when you're doing these calculations? Well, there is a formula you can use, okay? Now, I'm not going to go into how this formula comes about because it is quite complex and not really what we're aiming to achieve here, but it looks like this. Make that more. That is 1 plus I to the power of n minus 1 over the interest rate, like that. Okay, that is on your formula sheet, and it is known as the future value formula. Now, it's called that because if you think of it like this, if I put in $200 every month with this interest rate for 4 years, what will the value of the investment be in the future? Okay, what will it accumulate to? Okay, so that's why we call it the future value formula, because you're starting from nothing and you're calculating, well, what will it be in the future, okay? So if you put all of those variables in, like this, into your calculator, you get $10,000, $10,371.11, which is the same thing that we got in our spreadsheet here. Okay, so we know it's worked. Lovely. Okay. So that's your future value formula. Now you may also see a question where you have a bit of both happening. Okay. So both a situation where it's compound interest and the future value formula. So this would be if you started your deposit scheme with a lump sum of money. So let's say you started with $10,000 and you put in $200 per month and the same other values. I'm just going to keep those the same for the whole time so that we don't get too confused. Okay, so what would that look like? Well, you'd have to combine those two formulas. Like so. Okay, and you pop in all those variables you had before. Okay, so in here would be your 10,000. And then the rest of this would look exactly like it did before. And when you start with 10,000 and you earn interest on that, and at the same time you're adding 200 every month, earning interest on that, you end up with a grand total of $22,056.42. Okay, so that's a combination of the future value formula and the compound interest formula. Okay. Now, there might be some situations where you have to rearrange the formula. Okay, so an example of this might be something like you have a savings goal of $10,000. Okay, so you want to get to $10,000 in 4 years' time with that same percentage as before. Okay, and the question might be, if I want to get to $10,000 in the future, how much do I need to put in each month? Okay, so in that case, you can rearrange the formula like this. Okay, and by rearranging the formula, you work backwards to get, well, how much do I need to put in each month to get to $10,000? Okay, and if you put all that into your calculator, you get $192.80. Oopsies. $192.84. Okay, which makes sense because our answer from before took us a little bit over $10,000. So it makes sense that we would need to put in a little bit less. Okay, so that's the deposit phase. Okay, you've got your future value formula, combination of both compound interest and future value, and then at times you might be asked to rearrange that formula. Okay, that brings us on to our next part, which is just like there was a deposit phase where you're accumulating money, there gets to be a point where you can spend that money. So we're going to call that the withdrawal phase. Okay, so a lot of this kind of happens when, say, you're saving for a retirement fund. Okay, so over the course of your working life, you might be accumulating money into a savings account, and then when you retire, you can start withdrawing that money over time. Now, it's best to do that with an annuity, just withdraw a little bit at a time, because with the money still in the account, it's still earning interest. So you're still getting more money than if you took it all out at once and just spent it a little bit at a time, okay? So it's a good scheme, okay? So you are slowly depleting the account, but you're also earning interest on it, okay? So let's have a look at an example using those same values as before. So let's say you started with $10,000. Your interest rate is still 3.9%, and you want to withdraw $200 every month for spending money. What would that look like as a recursion relation? Okay, well, we can draw it like this. So that same interest arrangement as before. Okay, you're adding 1 because remember you are increasing by the percentage. Multiply that by the current term, but this time you're taking away $200. So you start with the term, you add the interest to it by multiplying, and then you withdraw your spending money, okay? Obviously, a 0 would be $10,000 in this case, because we've started with the lump sum. Okay, so can you see the difference? In the deposit phase, you might start with nothing or 0, and you're accumulating money over time by adding into it, making deposits. In this phase, you start with the big amount of money that you've presumably accumulated over time, and now you get to withdraw it and enjoy it. Okay, so if I turn that recursion relation into, once again, an Excel spreadsheet, you can see, here's my formula here, withdrawing over time. And you can see if I scroll down, that's going to take about 54, 55 months to completely deplete. Okay. And here's my graph. Once again, you can barely see that there's a curve happening here. Okay, but it is in fact a curve. So I have exaggerated it slightly in this graph here so you can see, yeah, that's what the curve looks like, because there are some graphing questions that you might encounter on the external exam. All right, so let's have a look at a question. We obviously don't want to use Excel again to do all these calculations, so once again we have a formula. It's a little bit different. Oopsie. You might see that n is a negative value here. That's usually what I notice. We call this the present value formula. Okay. The way you think, the reason we call it present value is because you sort of say to yourself, well, if I want to withdraw $200 every month with sort of these variables, how much would I need right now in order to do that over time? Okay, so how much do I need right now in the present to be able to have this money coming out each month for 4 years at this interest rate? Okay, so let's work that out. How much money do I need right now for this arrangement to work? Well, I want $200 every month. Here's my interest rate. And I want that for 4 years. Pop all that into my calculator, and I should get okay, so right now in the present, I need to put this amount of money, 8,800, blah, 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 into the account so that I can withdraw $200 for 4 years. Okay, so that's the present value formula. Okay. And this value kind of makes sense because if you notice back on our spreadsheet, it took a little bit longer than 4 years to deplete. So it makes sense that if you only want it for exactly 4 years, you would need a little bit less. Okay. Now, just like in the earlier deposit phase, sometimes you need to be able to rearrange it. Okay, so you might get a question that says something like, if I have $10,000 in the account right now, in the present, and, the same values as before, how much can I withdraw each month? Okay, so if I have $10,000, how much can I withdraw every month? Okay, well, you can see from the first one, when you had the the amount you were withdrawing, you could find the present value. Now we have the present value, we want the monthly amount. Okay, so let's rearrange the formula. So it's going to look like that. Okay, and you can pop all those variables into the formula. There's our interest rate. Pop all that into your calculator, and you should get $225.34. Okay. So when you're seeing questions like that, you're looking for keywords like withdraw or payment or things like that. Okay. How much can they withdraw if they have $10,000? Okay. So that's present value. So ways to think about it. Present value is in the withdrawal phase of the annuity, when you're taking money out, when you're receiving money. And then future value is when you're putting money in, you're in the deposit phase. Okay. Now, there's a special kind of annuity that's in the withdrawal phase, and we call it a perpetuity. Call it a perpetuity. Okay, perpetuity basically just means forever. Okay, so maybe a word you may have heard, you may not have heard the word perpetuity before, but maybe you've heard the word perpetual, okay, which means forever basically. Okay, so these are annuities that will last theoretically forever. Okay, so here's an example. If I had that same arrangement as before, I put in $10,000 and I've got that interest rate of 3.9% compounding monthly. If I withdraw just the interest that I earned, how much could I withdraw and keep the balance exactly the same? Okay, so if I take out just the interest, then the balance will never go down. Therefore, the annuity will last forever. Okay, so basically what I need to calculate is the amount of interest being earned on this amount and withdraw just that amount. And it will be the same every month, and my balance of $10,000 will never be depleted. Okay, so I just do this formula like this. If the withdrawal amount is going to be the value of my annuity, and I multiply that by the interest rate. Okay, so that's going to be $10,000 times 0.00325, because remember that's still got to be monthly adjusted. Okay, and if I figure that out, it means I can take out $32.50 every month, and the $10,000 will always stay there. Okay, not a bad deal. Okay, But you might also see this question rearranged. Okay, perhaps the question might be, how much do I need to invest now in the present value, if I want $40 every month and I want it to last forever? Okay, so this time I want $40. You can see I'm probably going to need a little bit more than $10,000. Okay, so I want $40. The interest rate is the same. Okay, how much do I need to invest in order to withdraw $40 every month and for my account to never deplete? Okay, well, in that case, it's the other way around. Come on, pen. Fun. Okay, we're back. So it's going to be A equals M divided by, so I've just rearranged that formula from before. Okay, so that's going to be $40 divided by 0.00325. And that means I have to start with $12,307.69. Okay, so if I want $40, I need to start with this amount of money. And in this arrangement, if I'm just withdrawing the interest that's accrued every month, then my balance never goes down, which is not a bad deal. Okay, there's just one more thing covered in this topic, which is a reducing balance loan. Which is a fancy name for something that you've all sort of seen before. Okay, this is how real life loans work. Okay, so when you were no doubt learning about compound interest back in year 11, you'd probably get a question like this. Someone wants to borrow $10,000, I don't know, for a car or something at 3.9% compounding monthly. They're going to pay off the loan after 4 years. Okay. How much will they have to pay back? Okay. And you would put that into your compound interest formula like this. And you'd get an answer of $11,685.31. And then presumably after the 4 years is up, this person just pays the entire amount back in one lump sum, okay, which is not really something that happens in real life. Banks don't really like lending people money when they're not actively paying it off, okay? Banks don't like seeing the loan amount increasing over time. They want to see that loan amount decreasing over time, okay? So if you've ever had any experience with a loan, or maybe your parents have talked about it, you are making repayments as you go along. You don't just pay it all off in one sum at the end, okay? You set up maybe a monthly, fortnightly, weekly repayment, okay? So this is not really authentic to real life. So what we would normally do is set up a repayment schedule, okay? So maybe we're going to, let me try that again, repay $200 each month. Okay, well, let's write that as a recursion relation. And so that's the interest charged on the loan, because the bank's got to have something on the side, okay? So that's their interest that they're charging, and that's you paying off $200 every month. So that's why they call it reducing balance. the amount of money in the loan or the balance of the loan will be reducing over time because you're making regular repayments, okay? And in this case, the loan amount is $10,000, okay? So the keen-eyed amongst you might have noticed that this is exactly the same recursion relation that I wrote for the previous section up here in the withdrawal phase, okay? See how it's exactly the same. And that's because it works exactly the same way. The only difference is this is talking more about an investment, your money that you're collecting interest on, whereas a reducing balance loan is money that you've borrowed that you need to pay off, okay? So just the framing is different, but it's exactly the same mathematics, okay? So you can use that present value formula to solve questions about loans, okay? So that basically brings us to the end of the sort of the theory stuff. I would definitely recommend that you practice questions with different values, different compounding periods, okay? I've used monthly this whole time, but don't forget there's also half yearly or semester or semi-annually, which would be 2 times per year, quarterly, there's 4 quarters in a year, so quarterly or each season. Monthly is obviously 12, fortnightly is 26, weekly it's 52 weeks in a year, and daily we go with 365, okay, in this case. So what you should do now is I have prepared some practice questions for you, okay? So what I'm going to do is put the question up. What you should do is pause the video, have a go at it, and then unpause it where I will be explaining the answer to you, okay? So have a go at this one. Olga invests $500 every 6 months into a fund that provides 9% per annum interest compounding every 6 months. What is the value of her investment after 10 years? So the first thing you need to do is figure out what is the context happening here. What sort of situation is this? Is this an investment or a loan? Okay, if it's an investment, is it the deposit phase or the withdrawal phase? If so, what formula do I need to use? And once I have the formula, what variable am I solving for? Okay, so pause the video, have a go. Okay, so the answer, the correct formula is this is the deposit phase, because you can see she's putting in money every 6 months. So that's the deposit phase. And we want to know what is her investment in the future. Okay, so you need the future value formula. So that formula there. Okay, if you picked the wrong formula when you did your question, pause the video again, have another go with the correct formula, please. Now the variable we're solving for is A. We want to know what it is in the future. Our monthly amount that we're depositing is $500. The interest rate is 9%. And we need to divide by 2 because it's semi-annually or half-yearly, however you want to say it. So that gives us a value of that. And 10 years with compounding periods every 6 months gives us a total of 20 compounding periods. If you pop all that into your calculator, you should get an answer of $15,685.71. How did you go? Okay, here's your next question. Once again, read it, figure out whether it is investment or loan. If it's an investment, is it deposit phase or withdrawal phase? And what variable are you solving for? Okay, pause the video, have a go. Okay, well, the answer is we need the present value formula, okay, because she needs to know how much to invest now in the present so that she can withdraw some money. Okay, so the formula you need is this one. Okay, and we are solving for A in this case. Okay, once again, if you put the wrong formula in, pause the video, have another go. So it's 3.3% per annum, and it is compounding monthly, so we need to divide by 12, which would give us a value of 0.00275. Our N value is 3 years worth of 12 months, which is 36 months in total, 36 compounding periods. If you put all that in your calculator, you should get $34,230.62. Next question. Pause the video again, have a go. Okay, so this one, as you can see, the keyword there was withdraw. How much does he need to withdraw? So you can tell this is the withdrawal phase, okay, of annuity. Now, there's also a keyword in here, stay the same. So this must be a perpetuity. Okay, so the formula you need is this one. Okay, if you chose the wrong formula, once again, pause, have another go. Okay. M is what we're solving for. Our interest rate is 7.68%. This is it as a decimal. It's compounding quarterly. So that gives us a value of that. The answer is, $8,640. Okay. Okay, next one. Pause the video, have a go. Okay, so the formula you need is the present value formula. Because you can see she has presently invested that amount of money, okay? And the other keyword here is receive. She's receiving money, therefore we must be in the withdrawal phase of an annuity. Okay, so you need the present value formula, but you can also see we're solving for a different variable this time, okay? So the formula we need is this one. Here are our variables. M is what we're trying to find. The interest rate is 0.035, so 3.5% as a decimal, and it's monthly. Now, if you put that in your calculator, you'll notice you get a sort of very long number there. If you round that number, because it's not terminating decimal, you will get a slightly wrong answer. Okay, so if you rounded at that stage and put that into your calculator, you are going to get a slightly different answer to what I get. So if you have a situation like this where it's not a nice, neat sort of terminating decimal, then just put it into your calculator using the fraction form like that. Don't round it. You will be slightly off. Okay. The n value is 5 lots of 12 months, so 60 months in total. Okay. When you put all that into your calculator, you get $6,367.11. So that's how much she will receive each month. And that will deplete the account. Here's your next question. Pause the video. Have a go. Okay, so you can see this must be a reducing balance loan question because they're borrowing money. Okay, now if you remember, the reducing balance loan formula is exactly the same as the present value formula. Okay, now the question is also asking for the repayment. So the formula we need is exactly the same as the previous question. Okay. And here are our variables. We are trying to find the monthly repayment. The interest rate is 0.063 divided into 12 months. We get a value of 0.00525. Nice, neat terminating decimal there. And 30 years, 12 months in each year. That's 360 compounding periods. When you put all that into your calculator, it's a monthly repayment of $3,373.40. Houses are expensive. Okay, second last one. Have a look. Pause the video. Have a go. Okay, so this one is one of those blended ones I was talking about where there is a lump sum to start with, which would be compounding interest, and the addition, the extra deposit that they're making every fortnight. So this is the one where you need this one. Oops, wrong variable. And then the future value formula here. Okay, and here are your variables. We're trying to find the total amount. We are putting in $150 every fortnight as our regular payment, but there's also a lump sum of $2,000. Our interest rate is 0.28, like that. And it's fortnightly, so divide by 26. Now that's going to give you another one of those weird numbers, so make sure you put it into your calculator using the fraction button. Sorry, that's a 6. Okay. And our number of compounding periods is going to be 6 years, 26 fortnights in a year. That's 156 fortnights. Okay. Put all that into your calculator and you get $27,831.22. Okay. Last one. Pause the video. Have a go. Okay, so the answer to this one, this is future value formula. He is in the deposit phase. Okay, you can see there's your key word there. Okay, now, however, it's asking for how much is his regular payment if he wants to get to this value in the future. Okay, so we need the rearranged version. Here are our variables. The future value that we want is $20,000. The regular payment is what we're trying to figure out. The interest rate is that. It's compounding weekly, so we have to divide by 52. That's another one of those don't round situations. And 5 lots of 52 weeks is 260 weeks. Pop all that into your calculator, and Eric will have to put in $69.96 every week if he wants to get to $20,000. Okay, that's the end. If you have any questions, please feel free to pop them in the comments. Let me know if there's anything you want me to go over in another video.